Hi everyone, so my name is Jean-Noe Morissette, and I'm here to talk to you about Ubisoft's experience developing with Vulkan, or how we like to call it, our Odyssey with Vulkan. See what we did there? All right, so first I'll start with a quick intro, tell you a bit about myself, and then I'll try to tell you who this talk is for. Hopefully the room doesn't empty out. So my experience, I worked at Ubisoft a while ago. I was working on Rainbow Six titles. Shipped a bunch of those, then went into medical simulation. It was like games for doctors. Don't tell them that. Then I went back to video games, worked on Arkham Origins, and finally worked on Assassin's Creed Odyssey, the port for Project Stream. I'm a flying architect at Ubisoft. So we're technical architects, usually look at problems look at an aspect of a production from top to bottom, beginning to end, and try to have a global view for the project. My responsibility as a flying architect is to try to find a slice of work that could be reused across multiple productions, and then find a solution for that and go from project to project to implement it. That's the flying part, I guess. And we also sometimes are used to tackle strategic priorities, like was the case for Project Stream. And now, who's this talk for? I see it as a bit of a follow-up or side-by-side to Dustin's talk from last year at GDC, where he was basically talking about taking Doom 3 from OpenGL to Vulkan. And he would talk about the challenges moving to a low-level API and all that. And he also has his blog. It's an excellent reference. But my talk's going to be a bit different. We had a DirectX 12 starting point. So we already had a lot of those low-level concepts implemented in the engine. And our endpoint was Stadia. There we go. We can start saying that now. So the talk is going to stay high level. I'm not going to show you. I mean, it's pretty late to be showing code anyway. And I'm going to try to. The other thing that's important to know is that we did this in a branch all the time. We went on projects. We were guests on those projects. We put a branch there and made our Stadia port. So we were trying to keep things fairly contained, so they would be easy to integrate back and forth. So sometimes our approach might look a bit convoluted, but it's because we were trying to just remove DirectX 12 and put Vulkan in there. So that's an important thing to keep in mind also. So now Stadia. I mean, I made these slides before the presentation this morning, so some of it might be familiar for those who've seen it. For those who haven't, then I'll give you my take on it. Basically give you my first experience with Stadia, what to expect from cloud gaming, what are the implications of cloud gaming, and give you a little overview of what the development environment is like. So my first experience with Stadia, I was in a meeting room, Ubisoft in Montreal, and they put a controller in my hand. And then I followed the cable at the end of the controller, and it went to a cell phone. And this was basically sending my input to a data center in Toronto where the game was running. And the game's output, the image, would come back through the internet. And I think the guy had a laptop on the projector in the meeting room. And I was able to play a fast-paced first-person shooter right then and there. And that was really impressive, so I was sold. And that's when I hopped on board. So what about cloud gaming in a nutshell? So you got a lot of that this morning, but basically, typically you have your console, your controller hooked up to it, your TV hooked up to it, and then when you want to play with other people, that's when the internet comes into play. But now, and the more people you play with, usually that could start, depending on the multiplayer architecture, but it starts taking more and more bandwidth to bring all that in. Whereas when we're talking about cloud gaming, what the user's bandwidth is used on sending his input to the cloud and then getting the image back from the cloud, getting a video stream. And what's interesting there is that what you would consider as your console, all the processing, the game, it's running in the cloud. And my early Rainbow Six days, actually, I was a network programmer, and when I look at this, it boggles the mind, basically. It means that the instances of my game can communicate between each other when we're doing multiplayer with very low latency and very high bandwidth. These are like data center connections between the different instances of the game. And for the user's bandwidth at home, he's always just sending input and getting a video stream back. Whether there's 10 people, 100, 1,000, it's the same bandwidth for him. So anyway, but we're not here to talk about networking, right? So going back to the implications of cloud gaming now. They touched on this morning as well, piracy. The user never has his hands on your files. He doesn't have your executable, he doesn't have your data, he can't crack your executable. He can't find out what the next DLC is by inspecting your data or whatever. All these files, all he's getting is a video stream. So all your files are actually in the data center where the game is running. So it's behind Google-grade security, and they're not getting their hands on that. And now, as for the hardware is not the user's problem anymore either. That's all in the cloud. So you don't need to upgrade it. You don't need to worry about the warranty. You don't need to worry if your Blu-ray drive is not sucking in the disk anymore, or the hard drive is clicking, stuff like that. You don't have any OS updates to worry about. You don't have patches to worry about. Everything gets done for you. Now, the trade-off is you have to deal with latency. That's the enemy number one when you're doing some cloud gaming. But who better to tackle this? Google, that's their bread and butter, right? It's dealing with latency. And they own the infrastructure for the cloud and all that, so there's many ways that they could tackle it as well. The development environment. So as you're developing for Stadia, you're going to have local instances of your game, so this is running on your internal network, or you're going to have cloud instances of the game, so you could actually run it in the data center. And what's cool when you run in the data center is that you benefit from the same automated build deployment that the final product has, right? When a gamer comes in, if there isn't a cloud instance ready for him, then they're going to deploy one super fast, and you're going to be able to play, right? He was talking about the 5 seconds. That's what I'm talking about. So you could modify your build system, say you're making your daily build, at the end of a build, to push that build into the cloud. And then all of your daily builds are going to be on there, and you could load any one of them in 5 seconds, right? So if you haven't synced in 2 weeks, you're working on a feature, and then you decide to sync, and you realize all the trees are blue or something like that, no problem. You could compare it to the current daily build to see if it's your code causing this, or if it's a problem in the build. And 5 seconds later, you're testing it. If you want to go in a meeting room and review some new gameplay mechanic, 5 seconds later, you're running it. All you need to carry around is a hyperlink. So this was a bit of a game changer. This changes, you don't have to lug these huge builds around and install them and copy them off the network and stuff like that. Another thing that's important to note, and it was mentioned this morning, is the GPU is AMD based. This is important for this talk in particular because I'm going to make a lot of observations about Vulkan, and you have to know where I'm coming from. My target is Stadia, so we would limit ourselves to AMD, basically. So we dealt with AMD drivers, AMD hardware. And this is not so much about development environment, but I got this asked to me by every team that was starting a new port, basically. Do we keep a PC Vulkan port around? Or do we consider Vulkan to be the API for Stadia and that's it? Or is it worth for us to carry that extra build around? And absolutely. It's not much work. In our case, it was one file, basically, and the swap chain, 1 page of code, it wasn't that much. It just uses different extensions and that's it. So it's virtually no cost to maintain, and you have a PC build there. And that PC build can be very useful. For us, what we would do is we divided the developers into 2 groups, and when they were on PC, on PC, we divided the developers into 2 groups. One gang had always the latest driver for AMD, so they release a new driver every month, and sometimes even more. Whereas with Stadia, you get your new drivers with the SDK, so they come in less often. And this would allow us often to, when we had a bug and we saw that only one of the groups was affected, then we knew that it could potentially be a driver problem. It was easy to identify driver problems that way. It came in useful more times than we thought. And also for SDKs. So you're going to get the SDK built for you. When you download the Stadia SDK, you're going to get the Vulkan SDK built for you. But it's useful to always have the latest one. And on PC, they're just so easy to fetch and install. And it's important to have the latest one to always have the latest validation layers. They keep improving them. They give you more information when there's errors. They catch more errors. So the validation layer was a very big part of keeping the stability and helping us with our port. So this was important to always keep updated. Then the Stadia toolchain itself, so I mentioned the Stadia SDK, everything that's open source in there, they also provide a patch that you can use to take the source code from the internet and then create a Stadia version of that locally. So basically, you could take your validation layer, you could take your render doc, add that patch on it, and then have a Stadia version. So if RenderDoc has a new feature and you want to try it out right away and you don't want to wait, well, you could just create your own version of RenderDoc for Stadia. No problem. So I'm gonna go through, so we didn't skip right into the Assassin's Creed Odyssey port. We actually started with the prototype before that. So I'll tell you a bit about that prototype. Then I'll tell you about our time on Assassin's Creed, and then finally the launch of Project Stream in a second. So the prototype was basically 3 people. We had 2 flying architects, so myself, Sébastien Lucier, another flying architect, and the project that we had joined had provided one of their architects to help us out as well. The project was basically prototyping some gameplay and stuff like that. They were using Scimitar Anvil. It was perfect for us. So we went in there, branched it, and started working on our Project Stream Stadia port. What did this mean, porting? Basically, we had to move everything to Linux, so the engine, make sure that everything built, everything ran. The external middleware, some of those middlewares we had libraries dating, versions dating from, I don't know, 2 years ago, and then you're running on the Linux, running after the Linux build for it and stuff like that. Our internal middleware, we would fix ourselves and then push it back so others can benefit from it. So there was a fair amount of work there, but a lot of the work went into the Vulkan port, adding a new API to the engine. But like I told you, we did have a DirectX 12 code path as a starting point. So that was excellent. The PC version of the DirectX 12 code path wasn't being used much. The tools on the floor, they were still using DX11. So it was a bit rusted. We had to sort of take some dust off it. But it was a good starting point for us anyway, because it has a lot of those low-level API concept already implemented for us. So that was on our side. And then the Stadia team, they were basically keeping an eye on us the whole time we were developing and trying to see where we had blockers, what was slowing down our iteration time. So they started off with a GDB debugger, and sending the executable and all that would take a lot of time to start debugging. So they replaced that with LLDB, the feature set of Visual Studio integration. They kept adding features to it, building up on that. The speed and stability of the overall experience, they kept improving during that entire prototype. And then Stadia and Scimitar aside, Vulkan itself, the ecosystem, the things we were dealing with, like the drivers, the shader compilers, all of this was fairly early days as well. So there were limits in the Vulkan limits that you could query in the driver on NVIDIA. So each driver had their strong points, their weak points, but we knew we were heading towards AMD hardware. So when we saw that we had problems with the limits, like descriptor set limits and stuff like that on the NVIDIA drivers, we set them aside for our port. We bring them back later though, if you're worried. So shader compilers were a big issue as well. Nothing was able to build our shaders. FXC was able to build them for DirectX, but then when we wanted to build our shaders for Vulkan and SPIR-V, we had to find a solution. So GLS Lang had just started supporting HLSL, couldn't deal with it. Even the DirectX shader compiler, it was the one we really wanted to use because we know we're heading that way anyway for DirectX. So it would have been great to have the same tool for both. But it also wasn't able to handle our HLSL. We have these systems called shader input groups. It generates a lot of code for our binding in HLSL and C++ headers. And the HLSL had tons of nested structures, and that was basically the first thing that they would have problems with. So we built ourselves a compiler, and we felt pretty awesome putting it together. We basically took FXC to generate the DXDC, and then we went to Unity's open source HLSL-CC library that converted all that to GLSL, and then with GLS Lang we could build it, and we would get SPIR-V. And it felt really good. We called it the VK compiler, packaged it all together. But even if it said compilation succeeded at the end, the SPIR-V it was generating wasn't always good. So we would have a lot of bugs. So we still spent a lot of time debugging our shaders. This was one of the big issues for the prototype. But all things considered, the prototype was done. We checked all the boxes. We accomplished everything we wanted with that. And then we figured, okay, let's move to a real production. So we tried to find something with a timeline that lined up with when Project Stream had to happen and all that. And we started working on Assassin's Creed Odyssey. So we were based in Montreal, and they were in Quebec City. And the Quebec City team also provided 2 programmers to help us, an engine guy and a graphics guy, and a project manager to also help us coordinate with all this. And otherwise, it was the two usual flying architects working on that. The good news also is that because we moved to an Assassin's Creed project, it was Scimitar Anvil, so a lot of the port that we had made for the prototype, we could just bring into the engine right away. And the objective was simple. Ship alongside all the other platforms, the same quality, same AAA experience, Assassin's Creed game on Project Stream. And I keep talking about that DirectX 12 port that we started from. You should go see Tiago Rodriguez's talk from a few years ago at GDC, moving to DirectX 12. He describes a lot of these systems. So I'm going to be talking throughout the talk a lot about the shader input groups and things like that. So you should, if you want to know how these systems work, you could just go to that talk. Still relevant. The nuts and bolts under changed, but the talk covers the purpose of the system, and that still remains relevant. And then finally, we shipped Project Stream. So it happened alongside all the other platforms, no problem. We shipped it with PC Ultra settings, and we had our solid 30 FPS everywhere, and it was public-facing, so everybody got to try it out, reviewers, gamers alike, and everybody got to weigh in, and it was mostly positive. And this is the internet we're talking about, and people had good things to say about it. They were even, sometimes we found that people didn't have much to say. They were just saying, well, it's Assassin's Creed, it works, it looks good, and they didn't know what more to say, basically. Yeah, there was one piece of information that was basically different from one article to the other, is the 60 FPS. Sometimes you would see 60 FPS, sometimes you would see 30. Like at the talk this morning, Stadia is capable of 60 FPS, no problem, but our game was running at 30. So the Project Stream was reported as its encoder and everything was 60 FPS capable, and it was, but our game was basically running at 30. And now, bird's eye view on Vulkan. So basically going to take you real quickly through the tools we had at our disposal while we were working on the port, and the documentation as well. So I told you about our shader compiler problems. Coming out of the prototype, that was the one thing we could all agree on. Shaders were a problem. We couldn't continue with that contraption we had put together. So Google's Stadia team basically shipped into gear. They put a couple of people together to help us out, to help develop DXC. They became the most responsive support team. Every time we needed something, we would get answers really fast. And actually, because they had sent an engineer on site, they had embedded a guy in our teams in Quebec City, spent some time in Montreal, and so we could just go to them with all our shader problems. And when we didn't have problems, they would look further ahead to make sure that, to try to make our processes better or to hit the problems before we do. So with all that effort, I'd say by the end of spring 2018, we switched our default compiler to DXC, which was a big thing for us. So the VK compiler was not our default anymore, so that felt good. And by the end of August, VK compiler got ripped out completely, it's destroyed. So if you see something called VK compiler, it sounds really official, but don't use that. It's not a real thing, it won't do you any good. Yeah, so we were full DXC by the end of the summer, and we were shipping maybe 1 or 2 months later, so we stopped upgrading our DXC at that point as well. But basically, bottom line, DXC is ready now. Go out there, use it. We upgraded it again a few months, maybe early in the year, so what, 4 or 5 months had gone by, and we had one bug, one regression. And 2 days later, we had a fix and a workaround, and we were running again. And the more of us use it, the more it'll be stable, the better it'll stay. The other thing too is while the person was embedded in our team, they would see us do things like the constant buffer layouts. We would try to, we had the shader input groups that was generating the HLSL header and the C++ for binding. So it wasn't so much of a problem for us, but our constant buffer had to respect all the padding and alignment restrictions that the GL imposes. So they came, and they found that annoying when they were debugging, and they asked us, and we're like, yeah, we find that annoying when we're debugging, but that's how it is. And they came up with an option for us in DXC, the use DX layout, so that allowed us to use the same headers in our DirectX 12 and our Vulkan builds. So that was cool. And there's many more of these options. You should really check them out when you set your DXC up, go read the documentation, go look at all these options. There's a lot of options to help you if you're coming from DirectX. RenderDoc. We all know RenderDoc. We all love RenderDoc. So This is one of the tools that we use on Stadia as well. They have a custom version of it that hooks up to your game instance and allows you to inspect draw calls, right? See what your textures are like, what the buffers contain. It's also very useful to debug the barriers. You can see the usage and frame panel there, and you can see everywhere that everywhere that you write to a texture, everywhere you read from it, and if the barriers are missing, you can debug that real fast. And what's cool also about the version that came in the Stadia SDK is that they added a VK code gen feature, which takes the frame you're debugging in render doc and generates a little C++ program that will render that frame. And that's very useful for optimization and a lot of experimenting if you want to try different things with your frame. I'll touch on that a bit later, actually, in the talk. The other tools, so I told you we were AMD based, so for profiling, we used the Radeon GPU profiler. So for all those low-level optimizations, know the cost of your barriers, your draw calls, your computes, see the occupancy of the GPU. You could also see your synchronization primitives, how things line up on in your frame. And finally, the last tool, the validation layer. And I said it was great, and I'll say it again, it's extremely valuable. Always use the latest version. It'll really help you out, it'll save you some time. Fix everything it sends your way. Sometimes we would ignore messages. When you do, just make it very specific in what it ignores, because if you make these big blanket ignores, you might be introducing bugs in your code and not know about it because they'll be hidden behind the messages you're skipping. But really, you should just fix everything. It's sometimes just getting to where the problem is and knowing, oh, this applies to me or not. You have all the information in hand to fix it at that point, so you might as well. Anyway, documentation now. This was my approach. I just went out there, got myself the Vulkan programming guide, and read through that. And it tells you how to set up Vulkan and then render your frame. And it's much less dry than reading the spec. They give you some context, they put everything in order. So that was good for me to get a good grasp of what's up with Vulkan. Or also Dustin Land's site that I mentioned earlier is a good reference as well. And once you have your bearings in Vulkan, then you go do your port, then you should have the spec open. And you should refresh it often, because they add stuff to it, and sometimes it's useful. No, most of the times it's useful. Sorry. And actually, there's some slides in this talk that between when I wrote the talk and when I'm giving it now, some things came up and some things changed, actually. Some new extensions came up. You'll see that later as well. When we got around the end for performance, we started going around trying to find white papers and talks about different optimizations that were done to Vulkan programs. And you really have to be mindful of where the information comes from. Vulkan is used for mobile and desktop, and if the person's talking from a mobile perspective, it doesn't mean it'll be useful for you in desktop, and you could be putting all that work and not get many results. Same thing goes, if somebody's telling you that something's good on an NVIDIA driver, it doesn't mean that it'll be useful on your AMD driver. So you always have to be careful where it comes from. And the best way, really, is just to use that VK code gen again. Just VK code gen, have a frame there, try to make that change that they're saying is going to help you, and see for yourself if it actually helps your frame performance before you start changing your entire engine to accommodate it. All right, so now we're going to get in the nitty-gritty of it. Vulkan in the trenches. So I'm going to talk about the different things that we were hitting along the way when we were porting, the differences with DirectX 12. So, yeah. So, I mean, and I'm guilty of this too. Like every time that people on other projects would come and say, so what's up with porting to Vulkan? You know, what's going to happen to, you have anything to tell us about? And everybody's always like, oh, allocation limits, oh, render passes. And, okay, it turns out it's not even that bad. Our engine would basically allocate huge chunks of memory and then sub-allocate. It was only certain debug modes that would be very generous with allocating constant buffers and this and that. And when we hit that problem, then we figured, all right, well, for our debug modes, let's just put in the Vulkan memory allocator. It's open source. It's provided by AMD. You can find it on the GPU Open site. And that fixed all our problems. And rather than run sometimes with it, sometimes not, and not know where bugs are coming from sometimes, and we figured, let's just always leave it on. We shipped it in retail. There was no big impact for us, so we figured, why not? So that problem was solved. It wasn't a big deal. Texture formats. Doesn't sound like much, but basically what's going on there? Well, RGBA 8, UNARM, okay, just change DXGI for VK, no problem. R32, you win, just change JCI for VK, and then you're porting, man. And then you got RG16 float, you just got to add an S float there. I see what you did, that's great. And then you got BC5, you add block at the end, that's cool. And then you're porting your A8, sure. So is it Alpha 8 or is, what are we looking for here? And then you don't have it. And then you hit this one format that has no equivalent. And I mean, you have all the mechanics you need. And you can just take an R8 and then swizzle the channels and do all that. But that means you need to then track those swizzles all the time. Actually, we went through 3 different solutions, and every time there was this little corner case bug that would happen somewhere. The best thing you could do is just stop using A8. But like I was saying, you don't want to, we didn't want to impact the production. If we start going in every shader and start changing the channels we read and all that, that might have caused problem for the team. So we were trying to find solutions within Vulkan, and every time it was a bit wonky. We had little problems here and there all the time. So a bit of time spent there. There were other little differences too, like we were in DirectX 12 and the 10-bit formats. We would be able to do them linear in DirectX 12, no problem. The same format in linear in Vulkan wasn't available. We had to switch formats around. It wasn't a big deal either, but it was just weird to see, I guess. Shader resources and descriptors. You're going to go from the concept of just considering images and buffers as resources to actually splitting them up. So when you have D3, D12 SRVs, well, instead you're going to have sample images, uniform textile buffers, uniform buffers. For UAVs, same thing with storage in front. So because we didn't want to make the split between image and buffer throughout the engine, again, we just removed the type on the pointers and carried an enum around it. So we were able from under in our Vulkan implementation to carry all that information around. It wasn't pretty. This is definitely one of the things that we're going to want to revisit and make an engine-wide change to accommodate. Other concepts as well, while you're porting samplers to samplers, that's great news. Vulkan can have them in the same table, but since DirectX can't, we just don't. Root signatures, descriptor tables, descriptor heaps is significantly different. You have layouts instead, you have your descriptor whites and all these things, but that code is so contained and so low level anyway that changing it from one to the other didn't cause that many problems. And it's just different concepts, but they're easy to grasp. It's just work that needs to be done, basically. And the resource binding in HLSL. There's some documentation on this in a DXC. You should definitely go read their examples, because mine is basically ... If you're saying B0, T0, U0, you're talking about 3 different registers when you're in DirectX 12. Fine. When you're in Vulkan, the type is ignored. So the resource binding doesn't consider the resource type, sorry. So when you're saying B0, T0, U0, if you ignore the resource type, then you get 0, 0, 0. So they're all referring, all 3 of them, to the same binding. So there's different ways to fix this. DXC offers command lines that says, okay, well, in Vulkan, when you hit a register type T, always add 100. And then when you hit a U, always add 200. And then you could space them out so that they never overlap. So T0 would be 100, U0 would be 200. Anyway, if it sounds convoluted, look into it. But basically, in our case, we had our shader input group compiler. So we had our shader input group system that generated the header. So we just changed the indexing in it, so it wasn't much of a problem for us. Render passes. Okay, so this is the horrible one, and this is the one that hurts. And yeah, if you want to use render passes the way they were meant to be used, and the way you're supposed to use them, then it's a fair amount of work, and there's nothing in our interface to accommodate this, and there's no concept like this in DirectX 12, and et cetera, et cetera. But as it turns out, the approach we took was basically to try to make them disappear. Like we tried to use them how they were supposed to be used, and then we're like, oh, how can we simplify this? How can we chop the problem up? And we ended up just putting our render passes really tight around the draw call. And by the time you're at the draw call, you still have cached here and there all the information that you need to create and begin the proper render pass. So that's what we did. Right before the draw call, we begin the render pass. And then we just leave it there. And if there's a call that can't be made in a render pass, we would just close it then. Or if we would get to the next draw call and the render pass is still there, we would verify if it's still appropriate. If not, we would close it and open a new one. So we were able to get away with this, and it basically made them disappear without much impact to our interface. Now, there's actually, so this was our first approach, and when we got to optimization, there's actually things that render passes are really useful for. There's information in there that the driver seems to use to make things go, make your calls go faster. It's not only for mobile. There's some people who say, oh, it's only mobile, TLS, and that's what pushed us actually to say, well, render passes aren't for us. Let's make them disappear. But it turns out we had some optimizations that we did for clearing and things like that, where if you're clearing outside of a render pass, then you add a barrier, it decompresses the texture, it takes a lot of time. Whereas if you do it in the render pass, there's no problem. And what we realized is the big challenge with render passes is if you put your clearing call is at the top here, and then you have 20 pages of code before you get to your draw call, how does that information carry over? What are you going to do there? But as it turns out, we could create a render pass with the clearing. It doesn't need to be a draw call or anything. We just end it right away, and it uses the fast clearing that everybody tells you to use. Every talk you go to, they're like, oh, clearing render passes is the fastest way. So we did it, and it really did help us out, especially for big textures. They say it also helps you for barriers, layout transitions, all that. We haven't tried that yet, but we're definitely going to make a pass once, well, all this is done now. So we're definitely going to make a pass to in the engine to better incorporate render passes and make the interface changes we need and bring them up, incorporate them in all our systems to get full benefits from them. Pipelines. Oh, I'm going over in time. Pipelines, quick overview. This is what makes these low-level APIs, this is what helps make them much faster, but creating them is slow. So let's have a quick look at creating our pipeline. So the build machine, your PC, whatever, you have your vertex shader, your pixel shader, you run that through DXC, you get your SPIR-V, and then you put that in your build. By the way, and then you bring the build back in either a cloud instance or a test PC. And by the way, this is why I was saying that keeping a PC build around won't cost you much time. Our shaders are kept in SPIR-V, which is still an intermediate language anyway. So it could, the same build, for us it was the only difference was the shaders, meshes, textures. They were all the same on PC and Stadia. So we're able to use the same build data to run on both. So we don't need to generate an extra build and spend all that time. And then moving along, your SPIR-V, you create shader modules out of them, and then you're rendering your frame, so you're setting all these states, and then you create your pipeline. And the different things that take time are basically the create shader module. This one's a bit weird. Like when we had, it's a thing we witnessed on AMD basically, where there seems to be some transformation to IL and stuff like that happening. So we tried to hide a lot of the creation of the shader module at the beginning of the game. When the game starts up, we try to do a big pass on all our shader modules to pay that price somewhere where it doesn't matter. So that one's sort of taken care of. Then we have the graphic pipeline. So what's at our disposal to accelerate that? Hello, Admiral Akbar. Word of the day is foreshadowing. This is how we create our pipeline. We have our shader modules and our render states, and we create a pipeline out of it. When we're loading a material, for example, we have a lot of permutations for this material, and a lot of them differ only by a couple of render states. So we could create the first pipeline, and when it's done, feed it when we're creating the second pipeline, so that it could reuse the shader module from the first one. And that's one of the parts that takes a lot of time, is converting that to IL, optimizing it, all that, and then you save some time. That's right. And all you have to do is when you create your pipelines, when you have the parent pipeline, there's a special flag you have to set. When you create the child pipeline, there's another flag that you set. Okay, and another way, oh, there it is. This information isn't always used. So it's in the Vulkan spec. You see it there, you're like, all right, I know how this works, I'm going to go implement it. And it turns out that AMD drivers, for us anyway, didn't use the information. So they optimize their pipeline creation in other ways themselves, but they don't use this that's provided by Vulkan. So we moved on to other things to try to accelerate our pipelines. The pipeline cache. The pipeline cache, again, uses all the same information, and then we create a pipeline. But you just provide an extra parameter to your create pipeline call, which is your pipeline cache object. And it verifies if for this input there's already a pipeline in the cache. Cool. If there is, then it shoots you that pipeline right away, and that's the fastest way to go. If there isn't, then it'll have to create the pipeline, it'll add it to the cache, and return you that pipeline. And once all your pipelines are created, you can take this cache and save it to disk. It's like for those of you who have never seen that, it's an SSD or something like that. once you have the cache there, the next time you're running, you can just load it up again, and all those pipelines are going to be ready, so all your pipeline calls are going to go super fast. Generating this cache, what we did at first, we just created ourselves a command line that would go through all of our data, load all of our materials, and create all the pipelines that we need. And at the startup of the game, create the pipelines for all our passes as well. So this would take a significant amount of time, so we have another mode where we just dump all this information into a file on the side so that then we could only process that file to generate a new cache. This could also be done through a layer. So we had built all of this into the engine, then realizing if we do it in a layer, we're solving the problem for everyone. So if anybody wants to be a hero. The pipeline cache misses now, and this was a problem. So we have our pipeline cache, and the pipeline cache is basically tied to your driver version, your hardware. So if any of that changes, then your pipeline cache, when you load it, will just get invalidated and won't use it. So, but it won't tell us. So when you make that call to vk create pipeline, you don't know if it used the cache or if it created it. All you know is you're getting a pipeline back. So it would be useful to have information regarding if the creation was a hit or a miss on the cache. And the other thing that, yeah, it's coming. So the other thing that would be useful is, say we have a full cache, and then on tomorrow's build, all that changed was 2 materials. So it invalidated 24 PSOs in the cache. Our options are basically to add the new PSOs and leave the stale ones there, or create an entirely new cache and create all the PSOs again. It would be cool if we could read the old cache, but then build the new one to sort of reuse the pipelines that are still good. Anyways, I'm just saying that. And then I was doing the post-final review like 2-3 days ago, and the guy sitting in front of me tells me, well, actually, there's a new extension that came out like a week ago or something, and it takes care of giving you that feedback of hit or miss on the cache. I'm like, but my talk is final. I handed in the slides, and what do you want me to do? He's like, dude, deal with it. So I just did this, and I'm going to keep going. Barriers. Barriers were a quick problem to solve as well. I'll just go over how we ported them, the optimization that we did on them, and then the initial layout, which is a little snag. Porting the, I'm really going to go over. Mostly, so we had an automated system, and because the only customer was DirectX 12, the system looked very close to, looked very much like DirectX 12. We would have user resources, it would insert barriers to transition between states, and it would batch all those barriers, which is an important part of it as well, because if some barriers are redundant, the driver is going to take care of collapsing that for you. And so as we were porting, again, we have to take care of that split between resources that become images and buffers in Vulkan. So we did the same kind of tricks that we did last time. We encountered it. And then you have to convert your DirectX 12 resource states into a collection of flags. And on the Vulkan side, there are access flags, pipeline stage flags, and if you need an image layout transition as well. So this wasn't so bad, and then so we put what we thought would be good, we ran with it. As the validation layer would report that we're missing flags here and there, we would just keep adding the flags until we had a clean validation layer. And I think this was the approach was fine because we wanted to get to something that works as fast as possible so we could deliver it to the floor. But when we came back to optimizing it later, if you just put these catch-all barriers everywhere, you're going to have a lot of full pipeline flushes that are going to appear, and you could waste a lot of time on barriers, and we've seen on other projects internally as well. So it's really worth going back with RGP, looking at what's happening, looking at the cost of your different barriers, and optimizing them. And when you're optimizing them, again, VK CodeGen, this is the best tool, is you just dump your frame, and then you see if I split this state into 2 different states so that it has less pipeline stage flags in it, am I going to benefit from this? And then you could just test it on your frame and see how it affects the performance. And now the initial layout. So in Vulkan, the initial layout is either undefined or pre-initialized if you care about what's in the memory. But so you can't do anything in these layouts. You need to transition to something else if you want to render. And you need a command buffer if you want to transition out of it. So when we were porting to DirectX 12, we found that there was a lot of spots like some of the passes that would create render targets and textures that were used during the pass that aren't filled from data. These parts of the code were in areas where there was just no command buffer. There was no reason. Even our abstraction, we would have devices. We'd have deferred devices. We'd have the main device, the compute device, and we had a creation device, which is a device that has no command buffers. That was the whole point. You can call it from anywhere, and it's safe. and you could use it to create resources. But at Vulkan, now we had to bring command buffers to all these areas. We had to get rid of the concept of the creation device and all that. So it created a divergent code path just for this platform. This was one of the, this one hurt a bit. Synchronization primitives. This is the end. We're nearing the end. So we have, I'm just going to go over real fast on what it looks like in DirectX 12, in Vulkan, and then what was involved in porting it, and our wish list there. So, DirectX 12 fence, you basically have one fence to rule them all. It could hold a value, you could signal it once, you could wait from the same queue, any other queue. You could use it to synchronize with the CPU as well. When you get to Vulkan, this is split into different synchronization primitives. You have the fence from when you want to go from GPU to CPU. You have events to synchronize workloads on the same queue, and then semaphores to synchronize workloads on the same queue or different queues. And it could only have two states, signaled or unsignaled. And when you wait on it, it unsignals it. So it could only be waited on once. And then what do we get? So the first thing was basically synchronizing GPU and CPU. That doesn't happen many places in a frame, so maybe at the end of a frame, maybe 2-3 debug modes. So it was easy to track them down, and we created ourselves a new class that was dedicated to GPU CPU syncs. So that one's settled. Not too bad. It was a cross-platform change, though. We created this class for everyone, but since it wasn't a big code change, we weren't so nervous about it. And now we're porting the different GPU workloads when we have different queues. So if we look at it in DirectX 12, we come into this with our fence with a value of 4, let's say, and it's done working on a command buffer, signals it to 5, and then we have 3 workloads that we want to start on 3 different queues, and they all wait for that signal. We wait on 5, no problem, everything works. But then when you get to Vulkan, you come into there with your semaphore unsignaled, you're done with your workload, you signal it, and then you have 2 workloads you want to synchronize. I could have put a 3rd one, but really. After the first one waits, your semaphore becomes unsignaled, so then the other workload has a problem. The good news is, the validation layer will catch this for you. In most cases, it'll tell you about it. So you'll know you have the problem, but now what do you do to solve it? We tried a lot of different things. We didn't want to go crazy on semaphores. We were like, oh, we don't want to allocate too many semaphores. But in the end, the easiest way to get where we were going is just have a semaphore per queue in our fence class, and then when the fence class would get signaled, we would signal all the semaphores that were in there so that every queue would have its own semaphore to wait on. Then you have potentially the problem where if nobody waits on it, then it remains signaled. So we would track the state of every semaphore, and if we would signal it twice in a row, we'd insert a wait in the middle, which doesn't sound great. And it really, when you looked at it in our GP, the thing was a Christmas tree. But we really got where we're going with it. The other thing is we still haven't dealt, I'm sort of going over on time, but we haven't dealt with the fact that you have the values. So you could signal on DirectX, signal 4, 5, 6, and then wait on 4 if you want. But then that means we needed to add more sets of semaphores. So we had semaphores like crazy. So our wish list, basically the Vulkan timeline semaphore would be perfect. It was announced back in September. It seems to have a lot of the functionality we need. It seems like it would reduce those 12 pages of code in our fence to the single page of code that we have in DirectX 12. This would be fantastic. Cross-queue events would be fantastic too, but I'm not going to get into that. So where we at, the work that we have in progress. The Project Stream demo when we shipped it was running on a single queue. And because the hardware was a beast, so we were running at 30 FPS everywhere anyway. So there was no reason to risk going to multi-queue at this point. But we did all that work, like you see, we debugged their semaphores and all that. So we're definitely gonna get back to that. Another thing that we saw happening is places where the GPU would read from host memory. When we would have a lot of this going on, it would start to bog the performance down. You should definitely look into AMD's bar zero heap. They describe it in GPU Open on their website. What we did is we added ourselves a flag, so when you create a buffer or a texture, you could tell it to allocate itself into this heap. And basically, while the CPU is creating your frame, as it writes the values in the buffer, they're going to get sent to device local memory. So the memory is host visible and device local, so you get to have your cake and eat it too. It's limited in size though, and that's why we didn't use it everywhere. We just went really when we had problems, we went and added the flag here and there. Other things to explore, 4K, HDR, can we get more frame rate when we add the multi-queue and all that? The NVIDIA support, the Ubisoft Bucharest team finished recently. I think it was a couple of weeks ago, we got the driver with the missing piece of the puzzle. So basically, NVIDIA support is back in. So that's it. Stadia is announced now. This is another platform that we're going to be shipping. So Vulkan's here to stay. Like I said, I was patching these things under, trying not to change the interface of the renderer and this and that. But now with time, we could have those changes start to surface and make their way up into high-level code as well. And I think there's a way to find a nice middle ground where Vulkan and DirectX 12 could live side by side together in our renderers. And the ecosystem has proven to us that it could ship a AAA title. We did it with Assassin's Creed Odyssey. Sure, everything's it's not always perfect, but it's open source, it's collaborative, we get to have an opinion in this, and we get to direct it, so I have no reason to believe that we can't get what we need as the new challenges arise. And yeah, that's pretty much it. I didn't do this alone, so I want to thank all these people, but now I'm short on time, but the names are there. I have time. Oh, snap, what am I doing wrong? This thing says, okay. So the other flying architect that was working with me all throughout this is Sébastien Lucier. The Assassin's Creed Odyssey team in Quebec was awesome. You see the names there of the 3 people I said they provided, but there's so much more. Anyway, I'm not going to start naming them all, but the team was super cool with us. The Assassin's Creed Origin team, as we were preparing Odyssey, Origin was winding down because they had shipped and they were done, and those guys gave us a hand as well. So Thiago Ulrich in Montreal, and everyone at Google that we worked with. There was tons of people involved. It was really cool every time we had a problem that you would meet a new specialist and this guy would help you out and solve a problem. So we met tons of cool people along the way. And that's it. So we have 10 minutes for questions. So the question is if I have any numbers to compare DirectX 12 to Vulkan, to compare the 2 ports. And no, I don't. I don't have them with me. We started doing these comparisons, but only on specific systems. We haven't done an overall comparison. So pardon? What do I have to share? And most of the time when we were running it on Stadia as well, so it was different hardware. Every time we would be on PC was just to debug things, debug particular things. So I don't have anything to share. I'm sorry, not on that. But we could come back with stuff later. So the question is, that VK CodeGen feature, can we have that on PC as well? Does it work? Is it Linux only, or is it? Well, I didn't say it, he said it. So it should be coming. Basically, they did it, they tested it, and we ran with it, and now that this is a proven thing, they're going to try to share it with RenderDoc so they could get integrated for everyone. So yes. Yes, it's on the way. Flat out, we have a definitive answer.
Hi, great talk. Thank you very much. Very informative. So the question is, when you were creating PSOs, how many PSOs were you pre-creating, and how much time did you spend building up PSO cache?
Okay, I guess I don't need to repeat the question, right? There's a microphone. So how much time were we spending on PSOs? How many did we have to create? Our cache had over 300,000, I think, PSOs, from what I remember. How much time were we spending on it? So we had 2 categories of PSOs. We have the PSOs for our passes and all that those are created when the engine starts up, and then we create all those PSOs. And then we have the PSOs for materials. So these are loaded on the fly when the game is running. So what we did at that point is we tried to create our PSOs from our loading thread. So the loading thread isn't critical to the render loop and all that. So it could tolerate the time of creating those pipelines. But we had so many that we were even choking our loading thread at that point. We were actually giving streaming problems. And we didn't just want to say, well, it's your problem now. So this is when we started working with caches. Because on other platforms, there were other fast paths to creating the PSOs that we didn't have access to. And that's why we started exploring the solutions that Vulkan offer. And pipeline caches were the best thing we found. We could have potentially created a pipeline cache per material, and then load pipeline caches and merge them in. And that would have added a lot of complexity, though. But it's something we had on the table that we never tried. So if anybody has experience with that.
I'll ask a follow-up question to this. What's the time to create one PSO for the most complex shader in milliseconds?
The time to create a PSO, the most time to create a
Like
PSO.
the average or most.
When it was heavy, the ones we noticed were could reach, like we would have a lot of them at a 10th of a millisecond, say. But then because of all the permutation of material, we could be creating 20 or 30 of them, and then that was just unacceptable at that point. And then if we were loading multiple materials, then we could actually reach sometimes half a second that we were adding to on the loading thread for a material. So a PSO, it would vary a lot, but you would get a really heavy one once in a while. It depends on the complexity of your shaders, I guess.
Okay.
Does that help?
Yeah, of course.
All right. Thanks, everyone.